question of life beyond the Earth is, in a way, a philosophical question. But for the first time, we are now able to address it empirically. Instead of answering the questions by sitting in our rocking chair, we answer the questions with the shovel and boots.
I don't dream at night about going to Mars. I actually have daydreams. And I think about just how amazing it would be to actually set foot on that planet and have a look around.
I want to go. I would like to be one of the people there on Mars and doing the science actually there on that mission.
Going to Mars would be an amazing opportunity. Mars has had a long and varied history which is just waiting there to be explored and unraveled.
3 scientists are helping to lay the groundwork for a human mission to Mars. It could take place within their lifetime. Their laboratory and training ground is in the Canadian High Arctic, in a place called Devon Island. In the middle of this frozen wilderness is a huge crater made by a meteorite that struck millions of years ago. The Houghton crater makes Devon Island the most Mars-like place on Earth.
This is the freezer, Darlene. I'm gonna go inside.
The staging ground for the Houghton Mars project is in California.
Okay, so this is 98-3.
Darlene Lim is a limnologist at the University of Toronto. She studies life buried in the sediment below Arctic lakes.
Okay, let me put this out.
Darlene has come to NASA to look at mud cores dredged up from the bottom of the lake on Devon Island.
This is a nice one.
The freezer is like the Arctic and like Mars, where everything is perfectly preserved. Ames Research Center is the scientific base for the Houghton Mars project. The scientists will spend 6 weeks on Devon Island doing biology, geology, and testing tools for future Mars exploration.
Ultimately, a human mission to Mars is what I sometimes call the mother of all camping trips. It's an expedition. You go somewhere.
Pascal Lee oversees the months of preparations.
You have to bring equipment to allow you to be productive where you want to go, to achieve your goals, and you have to come back safely.
Just getting to Mars will take 6 months. The first crew will be gone for 2.5 years. Staying in touch with Earth 100 million miles away will require a revolution in our communications knowledge. Stephen Braham from Simon Fraser University is one of the scientists blazing the trail. On Devon Island, he'll be testing wearable computers for future astronauts.
Basically what we have here is there's a computer wired into this, and there's batteries here powering this whole thing. And we've got a display. There's a little LCD display here projecting onto a mirror. I wear this thing, and to me it looks like I've got a full laptop screen sitting in front of me. I can see the whole screen, no problem. Doesn't look small at all. And then with the keyboard I can just kind of sit there and just work through it, and it's just like working on a laptop. I really can do everything I need to do.
Communications is the lifeline of a space mission. An astronaut exploring Mars will need to do many things at once.
Yeah, I can't imagine actually driving an ATV or some type of vehicle and trying to reach over and use the keyboard at the same time, unless you're just simply feeling suicidal.
We're not talking us that's going to be doing this. This is going to be our children who are great with computer games and can do 5 things at once without any problems.
Right.
I mean, you know, you might have a terabyte wearable computer and be able to have the entire mission database on it.
Where are you working this summer?
Hopefully we'll be looking at the far, because last summer we didn't get a chance to look at the far east of the equator, so that would be somewhere to look at.
At the University of New Brunswick, geologist Gordon Osinski, known as Oz, is plotting the coming field season with his academic supervisors.
Is that we now have in our meteorite collections samples of Martian material. This is making us realize that within our own solar system, material has been exchanged between planets.
They study meteorite impact craters, cosmic events that link all the planets in our solar system.
Develop our understanding of the hydrothermal pipe structures.
Essentially, it's chunks of rock crashing into planets, blasting craters kilometers deep. Mars and Earth have both been bombarded with meteorites. We now know that impact craters cover 2/3 of the Martian surface. By studying the geology of the Houghton crater, Oz can learn a great deal about Mars.
23 million years ago, a meteorite or an asteroid, probably about 1 or 2 kilometers in diameter, struck Devon Island. The result of this was catastrophic. The object which hit was hurtling towards Earth, at least 20 kilometers a second. The upper layers of sediment would have been vaporized. A big cavity was excavated, as much as 2 kilometers deep. This would be the same as detonating 3 or 4 million Hiroshima-sized atomic bombs in less than a second. The place would have just been decimated for hundreds of kilometers around.
Devon Island is been called Mars on Earth. It's one of the closest analogs to Mars that we have anywhere on this planet. We have a meteorite impact crater here in the middle of a polar desert that has created geology extremely similar to that which we expect to find on Mars. And in fact, NASA scientists have been here for the past several years and are here now in order to explore the region, in order to explore Mars by comparison.
The interest in this place did not come just from the impact crater. We also have valleys outside the crater and within it. We also have canyons outside the crater, networks of channels. All of these are features that might have counterparts on Mars. At least we see things on Mars that look astonishingly alike. There are ancient valley networks on Mars that have finger-shaped patterns to them. You find similar patterns here. Point is, we find not just one feature that is like Mars, but a wide variety of them, and things that have nothing directly to do with one another either. And it's this convergence of Mars-like features that makes one wonder, is there something that this place has experienced that is in common with Mars?
For the next 6 weeks, Devon Island is home to Oz and Darlene.
It does strike you as very Martian-like. The landscape is barren. There's lots of beautiful outcrops that I think if you were to just sort of wear a red, pair of sunglasses or a red lens, you could certainly imagine, being an explorer on Mars.
With 24 hours of daylight, the camp is up and running in no time. About 50 scientists rotate through the base. Many are regulars, a community of Mars enthusiasts.
This is pretty much the only moment that we have each day to sort of be all together here and share this time and all these comments.
Pascal, geologist and all-round space promoter, is the captain.
We come here to do, above all, science. We're learning about geology, we're learning about biology, life in extreme environments, the possibilities of life elsewhere. we are learning at the same time how to do exploration. To do that in a way that might be similar to the way we'd have to do it if we were to send humans or advanced robots to other planets.
It's amazing to work up at Horton because there's so much yet to do there. I've loved being outdoors ever since I can remember. And so for me, being in the Arctic, I can fit in there straight away.
Out in the crater, polar bears and muskox are the only other life the scientists will encounter. For Oz and Pascal, Horton Crater is a geological gem. Other craters are overgrown or underwater. Horton is well exposed. It's been preserved over time by the Arctic cold.
We think these are ejector blocks. They've come from probably a few hundred meters down at the time of the impact.
15 feet?
Oz is mapping sites in the crater where the aftermath of the impact is still in evidence.
Some of them have probably been thrown up and actually been airborne for part of their history. And others have sort of slumped and rolled down the cavity, the crater walls, to be sort of deposited here now.
It's interesting to see how big these things can get.
Yeah, yep.
Something that's able to move rock out of the way, create a bowl 20 kilometers across, and toss around chunks of rock the size of school buses. That is just astonishing.
I'm interested to compare these ejector blocks with the...
Every crater that you see on the moon will have ejector blocks sitting on their rims, and probably for craters on Mars as well. And so, to try to understand this phenomenon that is so common in the universe, we have to look at our terrestrial examples, and that's what we're doing here.
People ask me, what's your day job? This is my day job. That is the really, really cool thing.
Steve's background is in black hole physics.
Paid to prepare for.
He's always had big ideas churning around in his head.
Check the breaker right now. Katie's just waiting to kind of sniff out and run around in a second.
His accent can be hard to understand.
Okay, what next?
Steve has turned his mathematical genius to radio waves. He has built a complex network of satellite dishes and aerials so sophisticated that the campers can stay connected to their databases and labs at all times.
If you want to have scientists here in the base working with scientists in the crater, you need very good communication links that can do video, data, audio, really high resolution images. But once you start doing that, you bounce so many signals around that it messes up your radio transmissions.
On Mars, communications will be the single most important factor. If astronauts lose contact with Earth or with one another, the mission and their lives could be lost.
The thing is, we're in a crater here where the ground has been very distorted, where there's lots of rounded hills and topography that's very similar to Mars. And that distorts radio signals and makes it hard to communicate here. And that makes it interesting for us because it's a lot tougher to communicate here than other places on Earth in ways that are similar to Mars.
People are starting to recognize now that geologists will be going to Mars, and they probably will be at the forefront of a Mars mission. Even if we're looking for signs of life on Mars, it's probably going to be signs of past life. And as a geologist, we do that all the time anyway, looking for fossils.
Oz is always on the lookout for certain kinds of unusual minerals. For geologists, trace minerals are the first pieces of the puzzle in reconstructing a picture of past life. It has to do with what's known as hydrothermal activity. Within seconds of the impact, the Houghton crater filled up with glowing hot rock called breccia. Then a lake formed from rain and groundwater. The water eventually heated up to beyond the boiling point, dissolving the minerals in the underlying rocks. 23 million years later, mineral deposits are scattered around the surface of this crater.
Like when you first pick up something like this, you just think, whoa, what a beautiful mineral. Amazing. Just looks like ice. You find it in one place, but then you find it again and again and again. And then you start to build up this picture in your head of how it's distributed around the crater. Groundwaters interacted with these impact breccias which are lying around us were extremely hot after the impact, maybe up to 700-800 degrees Celsius. And when groundwaters and sort of rainwaters interacted with these hot rocks, hydrothermal activity occurred. Because all you need for hydrothermal activity is just a heat source and water.
The minerals tell Oz that this was once the setting for widespread hydrothermal activity. And where there was once heat and liquid water, there were also conditions favorable to life. For scientists looking for evidence of past life on Mars, Oz's research will help point the way. A few weeks into the season, the camp is settled into a routine.
Everybody is so focused right now on the task at hand. You know, for me, I plan, I talk with people about the day's activities, about where we went, about what we saw, about where we want to go tomorrow, and everybody's involved with that aspect of their day-to-day lives here.
This is an aerial view of the Houghton impact structure, and you can pick out the prominent grey, really pale grey deposits in the centre of the crater.
There's always the hum in the background, and somebody will all of a sudden say the word Mars, and in the conversation will explode.
When we look at all the things that life requires, the one requirement that life has that seems to be the limiting factor is liquid water. Now, when we look at Mars, we don't see any liquid water today. It's a cold desert world. But we see clear evidence that at one time it had liquid water. We see rivers flowing, we see what was clearly lakes, we even see what looks like oceans. So we see the traces of water past on Mars. And the interesting thing is that when Mars had water, Earth had water too, and life was just starting on the Earth. So Earth and Mars were similar during the period when life first started on the Earth. Was there life on Mars?
You'll come across a lake or pond, and sometimes you know that this has maybe been visited once ever before yourself by another human being potentially, or maybe never before. And there's so much going on in there that has never been explored that you're really on an edge that is very exciting, and you know that the next step is to start delving into what is going on within that water body.
Darlene and her PhD supervisor, Marianne Douglas, are tracing climate change in extreme environments.
What are the sort of the limitations of life? What can they withstand? And that's important to understand so that if we were to go to another planet such as Mars and look for life, we'd sort of know, whether or not there'd possibly be any microorganism still living there, and even where to go look for fossils of dead microorganisms, for example.
Beauty!
Woo! Yay!
The life forms in the core will tell Darlene how the climate has changed on Devon Island.
Super. Okay, I'll walk out. I'll go. Do you want? Okay. If Mars had water on its surface, some of that water may have actually pooled into crater lakes. If we're using Earth as an analog to Mars, then as we understand it, lakes actually accumulate sediment at the bottom, and that becomes a climate history or a climate record.
Great, we're doing it.
But the really neat thing from my standpoint is that all that environmental change is locked away, that secret is locked away in the sediment record of that lake.
Top centimeter is the cyanobacterial mat. After that, we go down into
Each centimeter represents several hundred years of crater history.
Centimeters down to about 10.
Darlene uses a hardy group of single-celled organisms called diatoms as her indicator of how the climate changed.
Diatoms are really interesting. They're microscopic organisms, they're algae, they're unicellular, but they also have this really interesting cell wall. It's made out of glass, essentially. And so in terms of preservation in the high Arctic and the sediment record, they're fantastic. Diatoms can serve as a wonderful source of information in terms of understanding how the environment and how the climate evolved in and around a lake or a pond.
Perhaps Mars will have creatures similar to diatoms. With cell walls made of glass, their signature would still be there in the sediment.
Someday we'll be able to send a robotic mission or a human mission to actually drill, take cores, and look at the environmental change of Mars and how it evolved through time. What happened to Mars? How did it become what it is today?
We're up here on Devon Island as part of a project to build a simulated human Mars exploration station here in the high Canadian Arctic. We expect to find out a great deal of what we need to know to explore Mars effectively.
The habitat, or the HAB, has been built a kilometer away from the camp. It's a model space capsule that serves as a base for the would-be astronauts. Steve has hooked up the HAB to his communication system.
HMP7 SFU, this is fix 1 to Pascal.
The field scientists are now connected to the HAB.
The idea behind the HAB is not to play astronaut. That's not why we're here. The idea behind the HAB is to provide a base from which we can start developing protocols for human exploration of Mars. Things such as simple explorations outside of this habitat will be a large production once you get to another planet that has a 95% carbon dioxide atmosphere, that has 1/3 of the gravity. HMP7 SFU, Pascal, I just heard that you are about to commence your EVA at 2 UTC. Is that affirmative? Confirm, over. We've got people from this crew out on an extravehicular activity, and what they need is somebody inside the habitat to actually support the communications and keep them posted on any imminent dangers, make sure that they're okay, record the time of departure, and record all their coordinates as to where they're exploring so that we can keep track of where they are, so that we're constantly in the loop in terms of how their EVA is progressing.
Oz and Pascal are deep inside the crater. Canyons and tall ridges separate them from the HAB. Their geologists' eyes are firmly on the ground.
It's like a library, you know? Each rock is a different volume, telling a different story.
Yeah, there's some really nice shatter cones.
Oh yeah,
here.
look at that.
This
That's
one's
beautiful.
like a perfect radiating cone.
Mm-hmm. This is a tool that we've come up with to try to collect rocks without having to bend down on the knees.
Yep.
Because the idea is that if you're in a spacesuit on Mars, it might be a very difficult thing to do.
Yeah, yeah.
Both because your suit is pressurized and also because of the weight of the suit. So.
get rid of these first. Yeah, it works really well actually.
Yeah, keep trying.
Yeah. Oh,
Using it.
HMP 7SFU, this is fix 1 to Pascal. Go ahead, over. HMP 7SFU, fix 1 to Pascal. I did not read. Please give me a count of 1 to 10, over.
The signal is supposed to get around those hills, but it doesn't.
I have a wonderful dish outside. It's absolutely a great dish. But for some reason, it's not working, and we still haven't tracked down why. And unfortunately, everything hinges off that communication link working. I don't know what's wrong with it, but my suspicion is that's got a problem. That little guy up there. If I can replace that, we'll be happy. It's really peculiar, though.
Fix 1 to Pascal. Did you just enter a canyon area, over? Pascal, I am barely reading you.
This is kind of weird.
Fix 1 to Pascal. If you can read this, just continue on your EVA. I'm expecting you in 3.5 hours maximum before I send out the search and rescue party. If you can, once you get up into higher ground, try and relay communications to us again. We'd much appreciate it, over.
Keep thinking I gotta find out there's some one little parameter that should have been flipped on and the whole dish would have worked, you know?
HMP 7SFU, mobile Oz, to fix 1. How copy? Over.
If this were Mars, the astronauts would now be lost. On Devon, they can make their own way back to the base.
There are a ton of things that need to be researched and taken care of before we can ever get anyone setting their feet on the surface of Mars. But you have to start somewhere, and you can't be daunted by the vastness of that entire project. It's fantastic to be part of this, and I think, you know, the day that somebody sets foot on Mars, it won't just be me that will still be keen to see that happen. The entire world will catch their breath and gasp the same way they did when they saw Neil Armstrong take his first steps on the moon.
This is not meant to be a real suit. It's meant to be a simulation suit. It offers an interesting aspect of discomfort and confinement and sort of general impairment. Things that would be very straightforward without this suit on become a lot more difficult, require a lot more thought. I'm fogging up like crazy, and this is a big problem, and it kind of impairs your vision, and especially walking on these rocks, it's always sort of tenuous even without your vision being impaired, so with even more fogging, it's really difficult to sort of maneuver around the rocks.
Darlene is not alone having trouble maneuvering in the crater. Bad weather has set in. All the science teams are having their share of problems.
Okay, Robin.
No, this is all from the pallet.
Oh, I see. Stand by. Stand by.
Stop the robot, please.
Over.
Sorry, that was my fault. My fault.
Steve suspects that it's the humidity that's wreaking havoc with his radio waves. He's sending for a new piece of equipment.
We just want safety. We want to make sure that any EVA team or any Traverse team coming out to the Halton Mars base can talk back to base.
It's Steve's last chance to put the project back on schedule for the season. Oz takes Pascal to see his most intriguing discovery. He's found sites where another kind of hydrothermal activity took place in the crater. After the impact, while the crater was still hot, steam and boiling fluids pushed their way through fractures. creating what geologists refer to as a series of hydrothermal vents. Cones made up of broken rock and crystallized minerals are the surface evidence of these underground pipe structures.
This is one of our hydrothermal pipe sites, right?
Yep. It's one of the better exposed pipe structures by the looks of it.
It's beautiful. Yep. And you've got this one mapped already?
Yep. You can see in here there's sort of cavities with calcite lining them. But yeah, some really nice textures to the calcite.
That's exactly it.
These calcite crystals were formed when the temperature was ideal for microbial life to take hold.
In these pipe structures, we see that all the rock is brecciated and fractured. And we're thinking that's due to sort of hydraulic fracturing, that these hot fluids and steams rising up these pipe structures, and when they hit the cooler rocks or the cooler groundwaters coming down, you get sort of explosive reactions going on.
The thing that's really astonishing is that they are so well preserved after 23 million years.
Yeah.
You can still see the delicate little crystals of calcite, as if the thing had stopped smoking and funneling fluids just yesterday.
Yep. Yeah, I mean, it's truly amazing.
This is just one of the most beautiful examples of hydrothermal pipe structures that Oz has been mapping. We're interested in finding these on Mars. There are many impact craters on Mars. These are places around impact craters that would have been warm and wet in the immediate aftermath of impact events. And where there's warmth and wetness, there might have been life. And so we want to understand where one would look for these things on Mars. Would you go towards the center of a crater? Would you just explore the surroundings, the periphery of it? And here at Houghton, based on our mapping so far, it seems like it's at the periphery of the crater that we find these types of hydrothermal pipe structures.
These might be one of the best targets.
Oz believes he's found something to help future Mars explorers.
Life in them.
Go to the pipe structures at the edge of the craters, he says, and signs of past life may be just below the surface. The new gear that Steve has ordered for his dish finally arrives.
We have a high-speed network connection, and that allows us to really start our big scientific technology campaign here. The next stage is we're going to form a radio network across the entire region. That radio network will link robots and humans into a network connection that goes back to Earth, as it were, and goes through a box that will actually completely simulate the link between Earth and Mars.
This is one of NASA's great hopes for future space exploration. With Steve's dish on the blink, it's been held up, awaiting its big moment.
We just had a little bit of waypoint confusion, and we're off and running again. Over.
Copy that.
With all systems up, the Carnegie Mellon team can finally roll out Hyperion, a shiny new robot loaded with artificial intelligence.
It's pretty fun to be out there.
Yeah, I'm looking.
Driving around. Does it feel like it?
Oh yeah,
It's good
I
to see it
definitely,
firsthand when you see the thing driving around.
definitely looking forward to going out
It's
there.
powered by the sun. On Mars, where there's plenty of sunshine, it would never run dry. Hyperion has a pair of eyes hooked to an electronic brain. It's charting a route across the Devon Island tundra and can see trouble spots ahead. This robot can explore for hours.
Right now it's driving itself, and we're just along as passengers, I guess virtual passengers watching what's going by. It's pretty bumpy up there.
Yeah.
Nothing dangerous, just
No.
bumpy.
Yep.
With unlimited power and a mind of its own, Hyperion could navigate great distances over the Martian landscape, scouting ahead of astronauts.
We can move around and look at the shape of the train, and you can see that it's really quite menacing.
The first robot on Mars traveled only 80 meters from the landing site. Hyperion opens up entirely new possibilities.
NASA's becoming a little more ambitious in the next 5 to 10 years with traveling farther, but we'd like to push that and go from tens and hundreds of meters to tens and hundreds of kilometers. And so the type of autonomy system that we have here is basically a first step in that direction.
Where's that?
Today is Steve's day of reckoning. His design for a full-fledged interplanetary communication system is ready for its big test. NASA Mission Control has been set up in California.
The data's just arriving back. We're looking at the images of rocks. We're listening to descriptions of what the scene was like from the astronaut team. It's wonderful. I mean, it actually is very powerfully telling us what the site looks like and what's going on.
This is Carol Stoker, and I'm reporting on the robotic exploration activities that were performed at Site 6 on July 30th.
Steve's looking at what you have to have in order to make communication from Mars to Earth work. It's a very, very tough job. There aren't many people in the world that can do that, and Steve does it very, very well. The biggest problem we're going to have comes from the fact that it takes 20 minutes for information to go from Mars to Earth and back. That in and of itself means that you can't really hold a conversation. For scientific missions, we've basically been on a mode of communicating once a day. So we send one set of communications up per day, and we get one set of communication back per day.
The simulation of how mission control on Earth could direct field science on Mars begins with a satellite photo. Mission Control requests more details of Site 6 in the crater. The astronauts dispatch a small robotic camera to get close-up and panoramic images. The images and sound travel back and forth over Steve's dish and radio links.
Site 6 is a very intriguing site. There's standing water down in the channel. Is it possible indications of biological activity? The stratification on these hills beyond are also very interesting. So both of those we'll probably have the team go look at.
The exercise allows Steve to test his wearable computers.
We proceeded generally uphill from...
They install the hardware in the spacesuit. Steve's radio network enables him to control the computer from his station in the hab. It's a big breakthrough.
I, as a geologist, I was needing a picture of this place taken 2 weeks earlier, and I was just able to call up these displays, and Steve back at the habitat was able to send all the information.
Surprising to me, we've been very good in a synergistic use of people here and in the field. So I think we've made immense progress, and what we're going to do next is really look at it in more detail to see what do we do next time to actually do this better.
And that's about it for what the rover activity was able to accomplish.
Yeah, we're just in the entrance to, I think, Shoemaker Valley. So we're in the canyon system. There's about maybe a 600-foot hill in between us and the crater. Over.
Oh, that's great. Cool.
I'll do another radio check in a couple of hours' time.
Steve's radio waves now reach into the deepest canyons of the crater.
Over and out. And clear.
We want to complete an entire map of the crater. Use this as like a blueprint, as it were, for searching for life hydrothermal systems and that on Mars. You need to take notes at each outcrop, and then like the big picture comes together later. The solitude up on Devon Island, especially within the crater, is something amazing, especially when you get away from camp and away from the generators. It is total silence. It's very sort of humbling being out there and just looking out into this crater and over this crater and thinking that, well, between you and the horizon there's nothing, probably no living thing out there. I guess you're going to have to cope with those feelings on Mars, but for me, I think it's a great feeling.
So Steve, I'm happy to see the connection is working well now, and congratulations for setting everything up at HMP. So how have things been going for you?
They've been going really well. We've had some problems with the weather, and we had some initial problems with the comms, but the comms are up now, and the weather's getting nicer.
Before the field season ends, Steve wants to review the summer's lessons with his partners at the Canadian Space Agency.
Logistics. Well, one of the biggest problems we're going to have here is understanding how radio waves behave on really dry ground. Mars is a dry planet. However, we've got a lot of wet soil here this year, and wet soil absorbs microwaves. So some of our data is going to be messed up by the fact we've got all this wet soil around.
First of all, it's good science, it's good technology. That's the most important thing. But also particularly about Steve's work is that it's helping to position Canada in a niche area where we think in the future we'll then be in a position that most other countries are not in a position. So when it happens that we need that kind of infrastructure on the surface of Mars, this is really giving us a head start in that discipline.
For 6 weeks, they've worked side by side, sharing research and daily chores. By departure day, they've become good friends.
There's several people in camp who really are people that want to go to Mars, truly want to go to Mars personally. And we'll sit there and we'll discuss it. We're sitting inside the crater especially, and you're in a place that looks like Mars. There's this emotional bond that forms between people because we're dreaming the same thing.
The people that do end up going to Mars are going to be sort of a different breed altogether. They're going to want to take that chance. And I think in that adventure, they're going to have to really find themselves.
The Houghton crater has given the science team precious experience in the quest for Mars. The next phase of the project will take place in labs and conference rooms back home.
From a technological point of view, we are much better prepared today to send people to Mars than we were to send people to the moon in 1961 when John F. Kennedy started the moon program. And we were there 8 years later. If we had decisive political leadership, we could be on Mars with people before the end of the first decade of the 21st century. It's just a question of political vision. It's a question of will.
At Ames, Chris McKay is also pushing for a human mission to Mars. He has big expectations of what we might uncover.
One of the things we now realize is that Mars, even if Mars had water and might have had life, it may be that that life was the same as life from Earth. That life started on Mars and came to Earth, or started on Earth and came to Mars. The planets may not be isolated from each other biologically. So it's not enough to just ask the question, was there life on Mars? We need to ask the question, was there a separate life on Mars? Was there truly a second, independent genesis of life?
The answer lies buried under the surface of Mars.
This is a very, very valuable piece of mud, piece of history that, to anyone may just look like a giant straw full of sand. But to me, this is a piece of history that's going to be great to look at.
Sometime soon, we'll drill a core from the Martian landscape. For now, Darlene uses mud from the crater to prepare.
It really is a really neat thing to actually start doing the analysis and see information pop out at you. You never really grasp how incredible it is scientifically until you come home sometimes.
Great.
Houghton Crater is a really interesting example of change.
Isn't that beautiful?
We've had the climate get a lot cooler and become what it is today.
If this were a core from Mars, Darlene would look for information about how the climate has changed on the planet. She would look for traces of tiny organisms similar to diatoms. They would begin to tell us what kind of life might once have existed on Mars. They might even tell us if we're alone in the universe.
The notion that what happened here on Earth might have happened somewhere else too, that there might have been an origin of life somewhere else as well, is not something that we've really thought much about. But indeed, that's the question. Was there a separate, independent origin of life on Mars? That's the question we want to know. If the answer to that is yes, that Mars had a second genesis, then in our own solar system, life appeared twice independently, then I think that's pretty clear that the universe is full of life.
Oz has brought back 50 kilos of rock and mineral samples from the crater. He's slicing them up to get a better look.
The scanning electron microscope can see right into the rock. And it also tells us the exact composition of all the minerals we see on the screen. We put our field work together with the more analytical side of things here, and together they give us this big picture.
Each season in the Arctic brings us closer to sending humans to Mars. The reality of that voyage has huge implications for those who will go.
2 or 3 years ago, if you'd asked me that I ever even stood the remote chance of becoming, let alone sort of going for astronaut training, I would have, probably laughed at you, I think. But now I'm starting to maybe believe in myself more and thinking that, yeah, maybe it is possible that I could fly in space one day. Then I'd want to know how dangerous it was. We've got 10, 15 years, so maybe we can combat the exposure to radiation and other things like that, which should make things relatively safe, in which case, maybe 2.5 years, yeah, we could handle that.
We have to learn how to do the missions faster, better, and cheaper, as they say. That's the key to getting to Mars. And part of doing it better is going to places like Devon Island and practicing. How do we do this? How do we make rovers? How do we make habitats? How do we make spacesuits? How do we test them on Earth where it's a lot easier and cheaper so that we've got it down? We know what we're doing, we know how to do it, and we can hit the planet running, so to speak.